In this video, we're going to talk about acids and bases. So there are a couple of different definitions that we use for acids and bases. One definition is the Arrhenius definition. So according to the Arrhenius definition, an acid is a substance that dissociates in water to give us H plus ions. And we frequently write this as H+, but in reality H+ does not exist by itself. In actuality, what we would have is H3O+, because H+ is very reactive, so it's going to react with water molecules and form H3O+ molecules. So we get hydrogen ions, or more realistically, we get hydronium ions. An Arrhenius base is a substance that gives us hydroxide ions in solution. So we frequently use this definition, and it serves us well in a lot of circumstances, but there's one small problem with it. The problem with it is that it doesn't account for things like ammonia that are actually basic. So if you measure the pH of an ammonia solution, you will find out it's a basic solution. So a more broad definition that deals with this problem is the Bronsted-Lowry definition. So the Bronsted-Lowry definition says that an acid is something that can donate hydrogen ions, or since H+ by itself is essentially just a proton, then we can say a Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base, on the other hand, is a proton acceptor. So we've removed the definition that a base has to have hydroxide in it, so that accounts for things like ammonia that do not release hydroxide ions but are actually bases. So when we deal with acids and bases, if we define things as proton donors and proton acceptors, then when we do a reaction, then we actually produce what we call conjugate acids and bases. So if we have a generic reaction, generic acid, for example, HA is going to be our generic acid, and we have our generic base. So our generic acid is a proton donor, and our generic base is a proton acceptor. When this base accepts a proton, now it has the same qualities as an acid. It is a proton it can donate. So now this can be a proton donor. So this becomes the conjugate acid. And our A negative, which lost its proton as it went from reactants to products, now can accept a proton if we went in the reverse direction. So this becomes a conjugate base. Oops. Not sure how we did that. Here we go. Conjugate base. So let's talk about how we define acids and bases. So we said that acids are proton donors and bases are proton acceptors, but then we also refer to things as strong or weak. So how do we define a strong acid versus a weak acid, and a strong base versus a weak base? Well, a strong acid is something that is nearly completely ionized in water. So we say completely ionized. In reality, things rarely actually go fully to 100%, but fairly close. So nearly completely ionized in water. For example, if we have something like nitric acid, if we looked at what we have at equilibrium, we have a high concentration of nitrate and H3O+ ions, and pretty much no concentration of nitric acid left. So these are 6 strong acids that you should have memorized. And we actually talk about these in the first semester of this course. So you're probably already familiar with these. But if you don't remember them or if you've forgotten, then these are the 6 you need to have memorized. These you should always recognize as strong acids: hydrobromic, hydrochloric, hydroiodic, nitric, perchloric, and sulfuric. These 6 will always go to nearly to completion. A weak acid only partially ionizes in water. So if we take something like nitrous acid, which is HNO2, so don't confuse nitric and nitrous. Nitric is HNO3, it's a strong acid. HNO2 is nitrous, it's a weak acid. So if we take a look at our weak acid is only partially ionized. So we have very small concentrations of NO2 and H3O plus at equilibrium, and still a fairly noticeable concentration of HNO2 at equilibrium. So here are some examples of weak acids. You don't need to have these memorized, although at some point you will likely become very familiar with the fact that acetic acid is a weak acid, since we use it quite frequently as an example, but you don't need to memorize these. Strong bases, much like strong acids, ionize nearly completely. That reaction of breaking down into the metal and the hydroxide ion goes nearly to completion. Your strong bases or your hydroxides are group 1 and 2 metals. Those will all form strong bases that will break down in solution into the metal and the hydroxide ion. Weak bases are things that only partially ionize in water. So weak bases and strong bases follow the same definition as strong acids and weak acids. So your weak bases are things like ammonia and some derivatives of ammonia, things like aniline dimethylamine. I would expect you to know that ammonia is a weak base. That's one that we will use quite frequently. The others you don't have to have memorized, but if you see something that has NH2 or NH in it, that's a good indication it's probably a weak base. So let's take a look at a few examples here and write some reactions with acids and bases. So we have H2SO4, which is sulfuric acid, and we're going to react that with water. So we want to write the balanced equation for the dissociation of each of the following acids in water. Acids or bases. In this case, we're dealing with an acid. So we have H2O, which is a liquid, and we're going to react our sulfuric acid with water. So we know one of our products, whenever we're doing an acid-base dissociation, is going to be H3O plus. And if we take a hydrogen off of the sulfuric acid, we're left with HSO4 minus as our other product. So sulfuric acid is our acid. Water has to be acting as the base. H3O plus is formed from adding a hydrogen to our water, so that would make H3O plus the conjugate acid. HSO4 lost its proton. So now if we went in the reverse direction, this could accept a proton. So that would make this the conjugate base. Let's take a look at an example with a base. So we have HCO3 minus as a base, and we're going to react it with water. So if this is a base, it's going to accept a proton, which means that we're going to have H2CO3 and that's going to be an aqueous solution. And if we take a proton away from water, all we're left with is OH negative. So in this case, HCO3 minus is the base. Water then has to be acting as the acid. H2CO3 was formed by taking a proton from water. So if we were going to go in the reverse direction, it would lose a proton. That makes it a conjugate acid. OH minus was formed by losing a proton from water. If we were going to go in the reverse direction, it would accept a proton. That makes it the conjugate base. So I'm going to let you do the other three on your own, and then we will get some more practice writing equations like this in class. So let's talk a little bit more about acids and bases. So what if we just have water by itself? Well, water actually undergoes a process we call autoionization. If you have water molecules, a very small percentage of them will react and form H3O plus molecules and OH negative molecules. That's a very small percentage. Most of your water molecules are just going to be water molecules floating around in solution. So we can write an equilibrium constant for this, just like we learned to do with equilibrium expressions. We know that we don't write liquids in the equilibrium expression, so we would only write H0 plus and OH negative. When we're writing this specifically for the autoionization of water, we refer to this equilibrium constant as Kw. So Kw is equal to the concentration of H0 plus and OH negative. So at 25 degrees Celsius, the concentration of H3O plus and OH negative in a solution in water is going to be 1.0 times 10 to the negative 7 molar. So if you plug that in, 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7, Kw at 25 degrees Celsius is equal to 1.0 times 10 to the negative 14. So we can actually use this value if we have the concentration of either H0 plus or OH negative and we want to find the other one. We can use Kw to do that. If we have OH and we want to find the concentration of H0 plus, we can take H0 plus is equal to 1 times 10 to the negative 14 divided by the hydroxide ion concentration and get our hydronium ion concentration. Conversely, if we had the H0 plus concentration, we can use that to calculate the OH negative concentration. So let's actually look at an example here. We want to calculate OH negative in an acid solution of lemon juice where H plus is equal to 2.5 times 10 to the negative 3 molar. So we know what the expression for Kw is, and if we rearrange that for the hydroxide ion, OH negative is equal to Kw over H3O plus, and we know Kw is 1 times 10 to the negative 14th. H3O plus means the same thing as H plus. They're just different ways of expressing that proton or hydronium ion. So if we plug in 2.5 times 10 to the negative third, so if we divide 1.0 times 10 to the negative 14th by 2.5 times 10 to the negative 3, we get 4 times 10 to the negative 12th molar. So that is the concentration of our hydroxide ion. Now let's try another one where this time we have to calculate H plus. So OH negative in seawater is 5.0 times 10 to the negative 16th molar. We want to know if the solution is acidic or basic, and we want to calculate our H plus concentration. So we have H plus, or H3O plus, since they're actually the same thing, although H3O plus is technically more correct. So H3O plus is equal to Kw times over OH negative. So Kw is 1 times 10 to the negative 14th, and we're going to divide that by 5.0 times 10 to the negative 6th, which is our hydroxide ion concentration. So if we take 1 times 10 to the negative 14 divided by 5.0 times 10 to the negative 6, we get 2.0 times 10 to the negative 9th molar is our H plus concentration. So the question also asks us whether this solution is acidic or basic. Well, our OH concentration is greater than our H plus concentration, so this solution would be basic. Another way we can determine whether something is acidic or basic is to use the pH scale. So the pH scale is a way to express small concentrations in a way that we like a little bit better. So instead of having all of these exponents, we can convert them into numbers that we're more used to dealing with, 0 through 14. So on the pH scale, pH is calculated as the negative log of the H3O plus concentration. So on the left here you see H3O plus concentrations. On the right you see the pH. So 7 is considered neutral. So that's the pH of pure water. Anything that is above 7 is considered basic. So this part of the scale is basic. So human blood is actually slightly basic. We're slightly above 7. Things like baking soda and ammonia are basic, and sodium hydroxide, which we're familiar with at this point. If we're below a pH of 7, we're acidic. So things like milk are actually slightly acidic. When you get down to things like lemon juice and coffee and tomatoes, we get a little more acidic. Soda would actually be down here on this end. Orange juice would be on this end. Stomach acid is acidic, and hydrochloric acid, which we're very familiar with at this point. If you have the pH and you want to go back to H3O plus, then we do the reverse. The reverse of taking the log of something is to do 10 to the power of that. So we do 10 to the negative pH. So as I said, a basic solution is a pH greater than 7, neutral is pH equal to 7, and acidic is pH less than 7. So let's take a look at a couple of examples here. The hydronium ion concentration for lemon juice is approximately 0.0025. And we want to calculate the pH of lemon juice with an H3O plus concentration of 0.0025 molar. So pH is equal to the negative log of H3O plus. So we would take the negative log of 0.0025, and if you plug that into your calculator, negative log of 0.0025, you should come up with 2.6. So for pH, I'm going to tell you, always go to 2 decimal places. That's just a standard that most pH meters will read to either 2 or 3 decimal places, but we're going to go with 2. So let's take a look at another example. We want to calculate the pH of an aqueous ammonia solution that has an OH negative concentration of 0.0019 molar. So in this case, we have OH, but we need H3O plus to calculate pH. So we need to calculate what H3O plus is, and we can do that using our expression for Kw. So we take 1.0 times 10 to the negative 14 and divide that by our hydroxide ion concentration. That gives us an H3O plus concentration of 5.26 times 10 to the negative 12. So our pH then is equal to the negative log of H3O plus. So we have the negative log of 5.26 times 10 to the negative 12. And if you plug that into your calculator, you should come up with 11.28. So in this example, you have to calculate H3O plus in a lake that has a pH of 4.5. So this time we're given the pH, and we want to know what H3O plus is. So we can calculate H3O plus as 10 to the negative pH. So we take 10 to the negative 4.5, and if you plug that into your calculator, you come up with 3.16 times 10 to the negative 5th. And because this is a concentration, we should have units after. So H3O plus will be measured in units of molar. So we have 3.16 times 10 to the negative 5th molar. So I'm going to let you calculate the pH of this solution. We have a 0.025 molar solution of nitric acid. So what I will tell you is that nitric acid is a strong acid, which means that because there's only one proton here, the concentration of the acid is also the concentration of H3O plus. So take the pH of this solution, and then we will talk about in class what the pH of the solution is. Here's another one for you to try. So how do we actually measure pH? Well, there's a couple of ways we can measure pH. One is that we can use something like an indicator, which is a substance that changes colors in different pH solutions. So there are different types of indicators. There are litmus paper that changes color. There's an old a red cabbage method that you can use to calculate pH. There are different indicators that change colors at different pHs. So those are all ways that you can determine pH. The way that we more frequently do it in the lab is using a pH meter. So a pH meter is a device that measures the electrical potential. What it does is it measures the electrical potential in voltage, and then it's able to convert that to H plus concentration. So you get a number that just shows you the pH, but your pH meter is still a little more work than that to get the pH. So we're actually going to stop here, and we will get some more practice calculating pH in class.